In this segment, we'll solve a second order ordinary differential equation exactly. We'll take the example with the distinct roots of the characteristic equation. So this is the second order ordinary differential equation which we're going to solve. And it has this as the forcing function, while these are the two initial conditions which we'll need in order to solve this particular problem. So let's go ahead and get started. Your full solution will be the homogeneous part plus the particular part. So if that is the case, then what's going to happen is that let's concentrate on finding the homogeneous part. So in order to find the homogeneous part, what we have to do is we have to look at the characteristic equation. So it will be 1 times m squared because the coefficient here is 1. And this is the second derivative, so m squared plus 5m because raised by 1 is the first derivative, plus 6m to the power 0 because the zero derivative will be equal to 0 is the characteristic equation, which gives us m squared plus 5m plus 6 is equal to 0. And I can factor it as m plus 3 times m plus 2 equal to 0. And that gives me the two roots of this characteristic are minus 3 and minus 2. You can very well solve this problem by using quadratic equation, and you will get the same two roots of the equation m squared plus 5m plus 6 equal to 0. So keep in mind that this particular lesson is for those who have already taken the ordinary differential equation course. So the homogeneous part will be k1 e to the power m1x plus k2 e to the power m2x because we have two roots of the characteristic equation. So we get k1 e to the power minus 3x plus k2 e to the power minus 2x. So that's what we get as the homogeneous part of the solution. Let's go and see what happens to the particular part of the solution. Let's go and recall the differential equation which we had. We had this as our differential equation. The homogeneous part of the solution which we just found out is of the form as follows. Let's look at what the particular part will be. The particular part will be the forcing function and all its possible derivatives. All possible derivatives e to the power ax are just e to the power ax. So what's going to happen is that we're going to get a e to the power minus 4x as our form of the solution, and it is not in conflict with any part of the homogeneous part of the solution, so we are okay there. So the question now arises that, hey, how do we find the value of a in our particular part of the solution? So we get second derivative of a to the power minus 4x plus 5, and the first derivative of a to the power minus 4x plus 6 a to the power minus 4x will be equal to the forcing function 7 e to the power minus 4x. And that's how we want to find the value of a. So the second derivative of this is 16a e to the power minus 4x. The first derivative of this is minus 4a e to the power minus 4x. So having said that, if we simplify the left side, we get 16 minus 20 plus 6 gives us 2. A e to the power minus 4x equal to 7 e to the power minus 4x. And that tells us that a is 3.5. So the particular part of the solution will be just a e to the power minus 4x, which is when we found a just now, will be 3.5 e to the power minus 4x. So we have found the particular part of the solution exactly. We have found the homogeneous part of the solution, but we still have to figure out what k1 and k2 would be. So that we'll do in the next slide. We found out that the homogeneous part of the solution is k1 e to the power minus 3x plus k2 e to the power minus 2x. The particular part of the solution we just found out to be 3.5 e to the power minus 4x. So the complete solution is the addition of the homogeneous part and the particular part. So for that, we will get this. So the question arises, how do we find K1 and K2? We'll find K1 and K2 by using our initial conditions. We know that y sub 0 is equal to 13. That allows us 13 by substituting 0 in our complete solution. So that gives us K1 plus K2 plus 3.5. And that simply tells us that K1 plus K2 is 9.5. And that's our first equation. By taking 3.5 to the left side, that's what we get as one of the equations. The second equation will be found by using the initial condition on the first derivative of the function. So let's go and see how that happens. So the next condition which we're going to apply is that the initial condition is on the derivative of the function at 0 is given as 17. So if that is the case, then let's go and see what our y is. Y is the expression which we have found out. So we have this as our y. Let's go and look at what dy by dx is. Dy by dx would be minus 3k1 e to the power minus 3x, minus 2k2 e to the power minus 2x, and then minus 14 e to the power minus 4x. This is just based on the formula that the derivative of e to the power ax is a e to the power ax. So that being said, let's go and apply the condition that at 0 it is 17. So this gives me 17. So we get 17 equal to minus 3k1, minus 2k2, and minus 14 here. And if we rewrite this equation by taking these two, the unknowns to the left hand side, I get 3k1 plus 2k2 equal to minus 17 minus 14 minus 31. That is the second equation. So now what we have is two equations, two unknowns in K1 and K2, and we should be able to solve them for those two unknowns. So let's go and see how we're going to do that. So we have 3k1 plus 2k2 equal to minus 31. That was our second equation. And the previous equation which we had obtained from the first initial condition was as follows. So what I can do is I can multiply this by 3. So I get 3k1 plus 3k2 equal to 28.5. So let me call it equation 3. So what I'll do is equation 2 subtract equation 3 from there. So if I do that, I will get minus k2 equal to minus 59.5. And that allows me to say that K2 is 59.5. Now if I substitute K2 in equation 1, what do I get? K1 plus K2 is 9.5. We just found out K2 is 59.5. That allows me to say that K1 is minus 50. So since I have now the values of K1 and K2, the complete solution is available to me. Y is as follows. And just substituting the values of K1 and K2 gives me and so that is the complete solution to the problem, which finds the values of K1 and K2 as well for the homogeneous part of the solution. And that's the end of this segment.